Welcome back to Arxflix. Today, we're diving into a fascinating paper that sheds light on the inner workings of in-context learning, ICL, in large language models, LLMs. This paper, titled In-Context Learning Creates Task Vectors, explores the mechanism behind ICL, a powerful learning paradigm where LLMs can learn new tasks from just a few examples. Here's a visual representation of the paper's central idea. ICL can be seen as compressing a set of demonstrations, S, into a single task vector, theta, S. This vector then modulates the transformer to produce the desired output for a given query, X. Let's break down this concept further. Traditional machine learning involves training a model on a dataset to find a function that best fits the data. But ICL presents a unique challenge. It's not clear how the model uses the demonstrations and the query to generate the output. This paper proposes a hypothesis class view of ICL, offering a framework to understand this process. The paper proposes that ICL operates within a hypothesis class, where each function is defined by a parameter vector, theta. This vector is derived from the demonstrations, S, and represents the task being learned. The model then applies this rule to the query, X, to produce the output. Here's how this works in practice. The transformer, T, is divided into two parts: a learning algorithm, A, that maps S to theta, and a rule application, F, that maps X to the output using theta. The paper proposes a specific implementation of this framework, where the first L layers of the transformer calculate theta, and the remaining layers apply the rule defined by theta to the query. To validate their hypothesis, the researchers conducted experiments across various LLMs and tasks. They separated the transformer's forward pass into the two components, and F, and evaluated the accuracy of this approach. This figure shows the accuracy for different choices of L, the layer where ends and F begins. Interestingly, all models exhibit a performance peak at a similar intermediate layer, suggesting that this separation is indeed a valid representation of ICL. This figure compares the accuracy of the separated approach to a regular forward pass and a baseline model that doesn't use demonstrations. The separated approach maintains a high level of accuracy, demonstrating that it effectively captures the underlying mechanism of ICL. The paper further investigates the robustness of the task vectors. They generated multiple task vectors for each task, using different demonstrations and queries, and analyzed their properties. This TSN plot visualizes the task vectors. Each task forms a distinct cluster, indicating that the vectors are stable and represent the task being learned. The paper also explores the interpretability of the task vectors. They used a vocabulary projection method to examine the top tokens in the distribution over the vocabulary induced by the hidden state. The results show that the task vectors often contain tokens that directly describe the task, even if these terms were not explicitly present in the demonstrations. This provides further evidence that the task vectors capture meaningful semantic information about the task. This paper provides a novel and insightful perspective on the mechanism behind in-context learning. It demonstrates that ICL can be viewed as compressing a set of demonstrations into a single task vector, which then guides the transformer to generate appropriate outputs. This work opens up new avenues for understanding and improving ICL in LLMs. Thanks for watching. Don't forget to like and subscribe for more deep dives into the world of deep learning. See you in the next video. Thanks a lot to Element for supporting Arxflix and providing this wonderful voice.